Hello, it's Keith here, and this is lesson 2 of the multi-platform series of my Z80 tutorials. Now today we're going to be using the code we wrote previously in the platform specific series to write a little tool that will take a set of 4 characters from the user by data entry. It will process and convert them to a hexadecimal value in the registers, and then it will show that memory location to the screen as a memory dump. So we will be able to use this for testing our programs or debugging them if we don't have very good debugging facilities available to us. Of course, along the way we're going to learn how to do text input, and this will include the backspace key so that the user can delete keys. We're going to convert lowercase to uppercase, and of course we're going to convert Ascii to hexadecimal for that memory location selection. Because this is a multi-platform lesson and we're only using the code we wrote previously in the platform specific lessons, this will work on all of our systems. So it's going to work on the Amstrad CPC, the Spectrum, the Sam Coupe, the MSX, the Enterprise, and even the lowly TI-83 calculator, which, as you can see here, despite its smaller screen size, is perfectly capable of doing this. So if we type just 4 digits, you'll see it exports the memory location here. And if we type 2 digits and then press the delete key here, you'll see it goes back 1. So we've got the ability to correct as well as to do data entry. And beyond today's hexadecimal memory dump example, we will be using this keyboard entry routine for some more interesting things later. So at the moment we're just using it to show off our memory dump program, but we will do more interesting game related things with the text entry tool later. So let's make a start. As always, all of the documentation for today's lesson is on my website, so if you prefer to read rather than listen, please take a look at that. Thank you very much. So, because it works the same in all the systems, we're just going to stick to the Amstrad, and you can take my word for it, it will work the same on all the other systems. Okay, so here's the code we're going to be looking at today. So today we'll be seeing how the memdump function works, which is our new memory exporting routine for sort of showing an area of the system memory. It'd be great for when we're testing programs and we need to just see what's happening and if what we expect it to happen is happening. We'll also be having a look at the wait string function, which will either read in characters until the user presses the enter key, or will read a limited number of characters, just depending on what we want to do. So we'll be having a look at those today. And also we've got a very simple uppercase routine, which will convert lowercase to uppercase, and an Ascii to hex pair routine, which will read in 2 characters from a string and convert them to a single byte in A, and we're using that twice to get a memory address here. Okay, so let's have a start then and have a look. Okay, the first thing I want to show you is I've added some more definitions here, and these are numeric definitions for the computer we're assembling to. You'll see there's one for each system, but only one will ever be 1, and it will be, this is the CPC header file, so only the CPC is compiled with a 1 here, all the others are 0, and the same kind of thing is happening on the other systems. So on the Enterprise this would be 1, but all the others would be 0, and so on. And this is for a section of code which is compiled conditionally but is compiled on multiple systems. This just makes it a bit easier for the WinApe assembler to do that, and we'll have a look at that later. So just a slight change to the header files here today, but generally everything is the same. Okay, so let's have a look at our memory dumper. So there's 2 ways we can run our memory dump here. The first is like this, as a call. So what we do is we call this monitor memdump command, and then we pass 2 parameters that will follow the call itself as a data byte and a data word. And the byte is the number of bytes we want the dumper to show, and then the word is the location that we actually want to display. And the reason we've done this rather than loading things into registers is we don't want to alter any of the registers if we can avoid it in our code, because we want our code to carry on the same way as it would normally without anything changing. Now the monitor memdump function will take the the calling address out of the stack, and will then work out what the following bytes in here were, and when it returns it will of course skip over these extra bytes. So the next command to occur after the monitor memdump occurs will be here after this again label here. So let's start and we'll have a look at this memdump command. So here it is. And the first thing we do is we swap the top item on the stack with HL. Now, of course, while HL will change, we can get it back later because HL's original value is now on the stack. And once we've run this command, what HL will contain at this point is actually the address of the function that called monitor memdump. So this is how we are able to get the following bytes after that call. So the first thing we do is we back up our registers that we're going to need. And then we load in a single byte from the address HL, which will be, if we just have a look at our, which will be this one here, which is the number of bytes we want to show. And we're loading that into C, and the reason we're using C is because we will be using B for the line-based loop later. Once we've loaded in C, we then increase HL to the next byte, and then we use the same kind of example we've seen before with our vector array code, where we're loading in A, then we're increasing HL, then we're loading in H, and then we're loading L from A, which loads in the HL pair, corrupting HL in the process, but only after we've actually got all the data we need. Now, we don't need to increase HL at all again here, because if you look at the bottom later on here, once we've popped HL, getting back the original calling address, we increase it 3 times, swap it back onto the top of the stack, so HL is restored back to its original state. And because we did these 3 inc HLs here, we will have skipped over these 3 bytes here. So that will put the stack back into the correct position for the return to occur and for no problems to occur there. And then the main bulk of this program is just running this memdump direct function and then pausing for user input. And this memdump direct function is the one that we actually call manually in response to user input once we've filled in the parameters from the user's data entry and from a default parameter based on our system screen size here. So memdump direct is actually the function that does all of the displaying on the screen of the memory address. Okay, so here it is. So the first thing we do is we show a label, which is the address we're actually about to show, and this is for when you were maybe you would be showing it multiple times for different address ranges. So it's just nice to have a little label of what we're actually seeing on the screen. So we only show it for the first line because of screen space limitations. Each line, as you can see on the normal systems, is showing 8 memory addresses. It's showing 4 on the TI-83 because the TI-83 is too small. And we're showing hexadecimal and ASCII because it can be useful to see ASCII characters if we're debugging. It gives us a good way of being able to see what the actual contents of the memory are. So we're doing both, but that does mean we are rather limited for screen space. So that just shows our label, and then we're on to the main loop here. So we're loading in the remaining bytes to show into A. So on our 16 character wide screen, we're only able to show 4 characters, but on our normal screens, the 32 or the 40 character screen, we're able to show 8 or more. So we're checking here to see how many characters are remaining to show, and then if there's less than we're able to show, we're going to show everything that's left. But if there's more than we're able to show, we're going to limit ourselves to the 8 bytes for the 32 or more character screen, or the 4 bytes for the TI-83 16 character screen. And then we proceed to here, and all we do is we subtract the number of bytes we're about to show, and then store the new remaining bytes for the next time the loop occurs. Now, we do the loop twice of showing the data, the first time in hexadecimal on the left-hand side of the screen, and then the second time in ASCII. So we push BC and HL, which are the remaining bytes, the counter for the line, and the memory address in HL. And then it's very simple from there on. All we do is we read a byte in from HL, show it as hexadecimal, print a space, increase HL, and repeat until B reaches 0, which is the end of the line. Then we restore HL and BC, and we're going to do the same, this time showing in ASCII. Now, depending on the system, we may not be able to show all the characters to screen because some of the systems have limitations where some of the characters have special functionality, and on the Spectrum, for example, the characters above 128 aren't a single character in width, so it would create a right mess. And this is where we're using these new numeric definitions that are either 1 or 0, depending on whether we're compiling to that system. Now, in the past, you may remember we've used the ifdef command, which, if something is defined, will compile the range, and if it's not, it will not compile it, or will compile the else range. Now, if with a numeric definition will compile if the value of the calculation is is not equal to 0. Now, because on the ZX Spectrum this will be defined to 1, and on the SAM Coupe, this will be defined to 1. This effectively says, if I'm either compiling for the ZX Spectrum or the SAM Coupe, then do this. And that will, and what this is effectively doing is saying, well, if you're trying to show a character over 128 on the SAM Coupe or the Spectrum, then swap it to a full stop, because those symbols are problematic on those machines. And then on the other systems, we're just comparing to character 32, because any character below 32 is likely to be a problem. So again, we're just going to show the full stop in those cases. But if it's not one of those characters, we just go ahead and show it as it is, straight onto the screen. And then again, move on to the next character and repeat. Now, on a 32 character widescreen, we'll already have reached the end of the line and started onto the next line. But on a 40 character screen, there's a little bit of extra space there. So we just need to put a new line at the end of those 40 character screens. And that's the Enterprise and the Amstrad CPC. So there's no problems there. Finally, we load in C to A, check if it's 0, and if it's not, we loop again. And that's actually all of our memory displaying function. That's it. It's there's quite a bit of code to it, but it's not that complex. And beyond the functionality of the memory dump, which you may quite correctly think isn't that useful, but please bear in mind we have also demonstrated how to read in successive bytes from after a call, which will have uses when you're very short of memory and you don't want to be doing register loads before a call, or when you don't want to be doing push pops because affecting the stack, or you don't want to be using the registers before the call for some reason. So definitely worth remembering there. So that's the functionality of the memdump as it is here, and it is down here in the memdump direct version. Now the next thing we want to look at is our new wait string function, which will read in a string from the user's keyboard, and it allows functionality of delete, and it allows functionality of enter, and it allows us to limit how many letters the user is able to enter. So in this case we're limiting them to 4, because any more than that won't make sense for a 16-bit memory address. So let's take a look at that. Here's the string reader, and here's our wait string function, and you can see I've written a little bit of documentation to explain how it works here. So we're returning C as the total number of characters entered, B will be the remaining characters, HL will be the end of the string, and we do add a character 255 to the end of the string, and DE is the start of the string as it was passed. I should just quickly show you. You do have to define a buffer for the user's data entry. You can see here I've got this one defined as test string. I've actually defined 16 bytes here. I actually only need 5 because we're requesting 4 characters from the user, and the function wait string does put a character 255, which is our end of string character. So you do always need at least one extra character, but just for safety I've put 16 here. So here we are. So we back up H and L into D and E here, and this is so we can do deleting later. We wait for the user to press a key. The wait char function returns the key in the accumulator A. We compare it to the enter key, which is defined in the headers of each of the systems. So you can just see it here. It does vary depending on system. If the user has pressed enter, then we jump to done here, which just puts the character 255 at the end of the string. If they have not, we then check if they've pressed delete, backspace. If they have, we run the special backspace function, which we'll look at in a moment. Anything else, we just store it into the current position of the array, increase the memory address that we're writing to, increase the count of the characters that the user's entered, print the character they just pressed, and then loop back here to carry on, assuming B hasn't reached 0 yet. Now the backspace function is actually surprisingly more complicated. So we've done a little trick here. What we first want to do is check that the user has ever entered any keys so far. So we want to check if C is 0. Now we could have done load A, C like we did just recently when we were checking if something was 0, but there is a bit of a shorter trick in some cases. If you don't want to change the accumulator, then you can actually increase C, decrease C, and then see if it's now 0. Increasing it, if it is 0 of course, increasing it will change it to 1, decreasing it will change it back to 0, and this will set the 0 flag without changing the value of C. So that is a nice little trick. It doesn't save any memory compared to loading into A and doing an OR A, but it does mean that you've not changed A. Now in this case it doesn't really matter, but I thought it would be a fun time and a worthwhile time for you to see that little trick of comparing a non-accumulator value to 0. So there we go. So if we've got here, then there are some values in the string. So the first thing we need to do is increase b by 1 because the user has deleted one of the characters, so we need to re-increase the remaining character count. Then we set the current location to 255. And then we decrease the location of the next letter in the destination memory address, and we put a space there, and this will overwrite the last character the user entered, and this allows us to delete it from the user's screen so that they can see that they still have more to enter. So we just load that into HL, and then we back HL up because we're going to do some things with the screen location. What we do is we use the getCursorPos function that we created before, and we use this. This will return the XY coordinates of the currently printing line of text. Now H will be the X position. We then subtract the current width of the string from H and store it back into H, and then we move the text cursor, effectively moving it back to the start of the string that we've just printed. We then print that string to the screen using the DE backup of the string's address. We printing it back to the screen effectively overtypes it all, removing the extra character that has now been deleted. We then do getCursorPos again and decrease it by just 1. This will then move the current text cursor over that space we just printed, and this allows the next key that the user actually wants to press to be printed in the right place. Finally, we decrease C here because, again, the user has now typed 1 less character because of that delete. And then we just jump back into our main loop here. And that's all we need to do to read in text from the user's keyboard and store it into a string in our 255 character terminated method. Okay, so we've now read in 4 characters from the user. The first thing we want to do is just load in the byte from the start of the string array. And we want to check if the user actually entered any keys. And again, I've done a little trick here. And what I wanted to do is to compare the first byte in the array to 255. Now, that would effectively mean that if it is 255, it effectively means there's no characters in the array. And rather than doing CP255, you can save 1 byte by doing inc A. If the byte is, if A is 255 and you do inc A, it will reach 0. And in that case, we know that the user has entered no data. Now, of course, we could have done a comparison to C here because C does actually return the characters. But again, I thought this was a nice time to show that little trick of doing a CP255 by doing an inc command and then using that 0 flag again. So now we start a new line just to clear to get past the text the user has entered. We now use this toUpper function, which we'll have a look at in a moment. This converts all the lowercase letters to uppercase letters in the string that HL currently points to. And we do this because our hex pair function can only cope with uppercase letters. So then we call our Ascii to hex pair function. This requires HL to be pointing at the current memory location of the string. It will convert 2 of the characters to a hexadecimal pair in A. We store that in D. We run it again because each time we run it, it actually increases HL by 2. So this will get the next 2 characters, and then we store them in E. We then exchange DE and HL because our monitor memdump wants its memory address in HL. We set the appropriate number of characters to show in C, depending on the size of the screen, because the Ti-3 can't show as many characters. Then we just run the memdump and we loop right back to the top. Now, if at any point the user doesn't enter any characters, it will actually abandon. So you can see here, I can enter another string here. But if I hit enter, it returns back to basic. Okay. So we've had a look now at how our memdump works. We've had a look at how our string reading works and how we're actually treating it. So the only thing left to look at is these simple little string functions here. So the first one is the toUpper command. We're just going to process through the HL addressed string here until we get to a 255. We don't do that inc command here because we are actually using A again here. Remember that inc command would actually change the value in A. So it's not appropriate when you're going to use that value in A for later functions as well. So here we do the CP255. First we check if it's less than lowercase a. If it is, then we don't want to do anything with it. Then we check if it's greater than the character above lowercase z. If it is, then it's not in the range we want to do anything with. if we're in that range, then we're between lowercase a and lowercase z. All we do to convert it to uppercase is subtract 32 and store it back where it was. And then we repeat around until we get to that character 255. Very simple. And so now ASCII to hex pair. So I've written this ASCII to hex function here, which will convert one character to a byte. And all we do here is we shift the bits left, effectively moving the low nibble to the high nibble. We then store it in B. We run it again to get the next character, which will be the lower of the two nibbles. We then OR in what will now be the higher of the two, and then we return back. And let's have a look at this ASCII to hex function here. It's very simple. All it does is it loads in a character to A, increases HL for the next read, and then we subtract 0, the character 0, from the value in A, which will sort us out for anything between 0 and 9. Now, if we're A or above, then we actually need to do some more work. But because we've already subtracted 0 from here, I'm actually subtracting 0 from the compare here. Now, if we're below that, we don't need to do anything else. But if we are above that, then we need to offset it to make the letters A and above to A to F. So I'm actually doing something quite tricky here. I'm actually subtracting 0 from A, which will get the start of the range we're changing, and then subtracting A from that in hexadecimal, which is the addition we want to make to it. Now the effect is that 0 to 9 in characters will be converted to 0 to 9 in numbers. A to F in characters will be converted to the valid hexadecimal, but it should be noted that any other characters that are entered into this function will malfunction. There's no checking to check if you've put a G in or anything like that. Now you could argue quite justifiably that that's rather a major flaw with this. Yes, that's certainly true. Because I'm only using this to show characters to the screen, I'll just show you. So if I put G, 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 okay, it's showing the wrong memory range, but what I've entered doesn't make any sense. I could have put in filtering either at the ASCII to hex function or even better at the string reader function, but if I had done that, it would have made either of these functions larger. My current plan for them is just to use them as a debugging tool, and because I'm only reading data and not writing it, the fact that misentered data is showing a wrong range of memory isn't a problem. So that's definitely something you want to consider as a limitation of these functions that you could quite easily fix if you felt the need, but it's not a limitation that's going to cause us any problems in the example we're seeing today. Now that actually covers everything I was planning to show you today with these functions. I know we're still at a very early stage here, but I do have a lot more planned for these string reading functions in the following weeks. Next week we're actually going to look how to process those strings and do comparisons so we can take text-based commands from the user, and we're going to develop that quite a lot further in a way that I think you're going to find quite enjoyable, and maybe will give you an idea for a game you can develop using my functions, and I think we can take it quite a long way. So please like and subscribe if you want to see more of this. I'm hoping I can show you some really nice things coming forward. I've got a lot of other things I'm working on with this series that just aren't finished at this stage yet. So please don't think that just because we're showing relatively basic stuff at the moment means we will always be doing relatively basic stuff. And as I've said before, the example you've seen today does work in exactly the same way on all of the systems. So what you're learning today may look quite simple and quite crude. Well, yes, it is, but you're learning it in a way that will allow you to develop one game for 6 systems if it's a very simple text-based game. And I think that's really something that's quite remarkable and quite exciting. And I hope you'll follow me as we do more with it. Thanks for watching today, and goodbye.